Imagine this. You're asleep, at home, at night. All of a sudden, a man bursts into your room and says, "We need you in support of your country." Well, other than being a little bit bleary-eyed, you might say, well, what are you talking about? What do you need me to do? That's classified. We can't tell you until we know you're up to snuff. So he blindfolds you, and he puts you into a truck, and he drives you who knows where for about 4 hours. While you're blindfolded, bored in the back of this truck, in your head, you start graphing, because nothing excites you more than mathematics. You graph your velocity as a function of time. First the truck speeds up, and then it slows down. Then it speeds up, and you're capturing all this in this little graph that's in your head. Finally, after 4 hours of this kind of driving, you're pulled out of the truck, and the government agent says to you, "So, where are you?" Well, it's a good thing you were playing around with math in your head. So you sit there and think, what do I know about motion? You say, well, okay, if I define a variable x as my position as a function of time, then I know that the derivative of x with respect to time is the rate of change of my position. And this rate of change is going to depend on time, and it's going to equal my velocity. The rate of change of my velocity is also going to depend on time, and that is my acceleration. Well, I plotted my velocity as a function of time. So if I took the derivative of this plot, I could get my acceleration. But he didn't ask me how fast I accelerated. He asked me where I was. So I know my velocity, and I need to find my position. Well, if I multiply both sides by dt and integrate from my starting time and point to my ending time and point, I get the integral of the velocity with respect to time is equal to my end position minus my start position. So all this means is that if I have velocity and I integrate it over some period of time, it's going to give me the distance that I went. This is a good start. I could then write that my current position is equal to my beginning position plus the integral of velocity that's in my head right now. So the integral of velocity with respect to time between when they pulled me out of bed and now. That means I'm looking for the area under this curve in my head. So how can I do that? Well, let's first say that my velocity as a function of time is this function, f of t. So it's minus t minus 1 squared plus 1 for the first 2 hours. During that second hour, from time t equals 2 to 3, my velocity was equal to t divided by 2 minus 1. That's when I was speeding up again. Finally, between t equals 3 and t equals 4, that last hour in the van, my velocity was equal to 1 minus t minus 3 cubed, all divided by 2. So can I use this information to find the area under this curve and thus my current position? So let's recap what we know. I started at a position 30 miles north of town because that's where my home was. And I know that my end position was going to equal my start position plus the integral from when they pulled me out of bed until now of my velocity as a function of time. So my velocity as a function of time looks like this, and the function equals this three-parted function. So let's try to calculate this integral. Because I have 3 different equations for those 3 regions, I'm going to split my integral up into those 3 regions. So I've got the integral from 0 to 2, from 2 to 3, and 3 to 4, or now. So let's solve these 3 integrals. The integral from 0 to 2 of minus t minus 1 squared plus 1. If I integrate minus t minus 1 squared plus 1, I get minus 1 over 3 t minus 1 cubed plus t. This plus t comes from the 1. 1 over 3 t minus 1 cubed comes from the polynomial rules that we know. So all of this I'm going to evaluate from 0 to 2. My second term is also a polynomial. So I have t squared divided by 4 minus t. Because if I take the derivative of t squared divided by 4 minus t, I get back t over 2 minus 1. I'm going to evaluate this from 2 to 3. My last term is still another polynomial, even though it's cubed. It's just a higher order. When I integrate that, I get t minus 1/4 t minus 3, all to the fourth power, and all of these terms divided by 2. I'll evaluate this from t equals 3 to t equals 4. If I plug all of those in, so I evaluate my first term from t equals 0 to 2, my second term from 2 to 3, and my third term from 3 to 4, I get a rather long equation, but there are no variables here. I can solve this out. When I do, I end up getting 47 divided by 24. So remember, this is equal to the integral from time equals pulling out of bed to now of my velocity as a function of time. So I can go back and plug that in. That's 47 divided by 24 miles from my current position. If my current position was 30 miles north of town, and I've gone another 47 divided by 24 miles north, then my current position is about 32 miles north of town. So let's review. If I have x, which is position, as a function of time, then I know that the derivative of x with respect to time is equal to my velocity, because that's the rate of change of my position. If I integrate my velocity over some set period of time, that's going to give me the change in my position over that period of time. So I can use information about my beginning position and my velocity as a function of time to end up with my current position. By knowing all of this about motion and dynamics, we've managed to convince this man in black that we are up to the task of saving the country and saving the world just by knowing a little bit of calculus.